This lecture deals with determination of a Ka value of a weak acid. When a weak acid reacts with a strong base, a salt, sodium acetate, and if we're using acetic acid, and water are produced, we can use a titration trend and the data derived from that trend to determine the Ka value. Now, in the process of titration, we'll be adding the base into the weak acid, the acetic acid, and it will be following this process. Now, to understand how to use this approach, you need to understand that before we start titrating, the pH of the acetic acid runs in about 3. Take that back. Log of the Ka value is 4.7. So 1, 2, 3. We're starting right in here. Let's call that 4.7 pH is our starting point. Now this is 100% acetic acid in solution. So we need to make note that the solution is all acetic acid. None of the base has reacted to produce the salt. Now, and what we'll do is add portions of the base into the acid until we monitor the pH as a function of volume that we add, and we'll generate a pH curve. So as we start, we open and we put a little small amount of base into the solution, and we neutralize a couple of dots, so to speak. So we still have a large amount of acid, and the limiting reagent, of course, is the base. Now, as we go along, we continue to add some more base. We neutralize some more the acid, and so we're moving along. And so this would be more toward the basic. So we'll start generating a titration curve that begins to follow this trend. As we add more, we neutralize more, and we get closer to the pH, basic pH. And we add more, we neutralize more of the acid. And so we come down in here, and so we keep going, and we keep going right in here, and then at some point we start moving through the equivalence point, and so we're almost neutralizing. We keep adding, and we go through an equivalence point right here, and finally we go through the equivalence point, and anything beyond the equivalence point is extra base. So if we added any more base to the solution at this point, it would not react with anything, and therefore contribute only to increasing pH values going up this way. So it would follow a trend like that. So if we connected our dots, we would have a pH curve, titration curve, that would follow this trend right through here. Now, the equivalence point of a titration of sodium hydroxide into a base. For a titration like this, you will find the equivalence point about 8.9 in acetic acid. Now, to use this data to determine a Ka value, what you have to do is realize that we're going to use the point that's halfway between the equivalence point and the beginning of the titration. Understand here that before titration we have 100% of acetic acid before any of the base has been added into the reaction. At equivalence point right here, there is no original acetic acid left. So we've neutralized all of the an original acid. So at the 8.9 equivalence point, we have 100% base OAC minus right there, and 0% HOAC. So all of the acid has been converted to salt at the equivalence point. So the reaction then is used to, the acetic acid reaction, or the hydrolysis reaction is used to determine this pH. Now, to understand how to get the Ka value from this right here, what we do is take the weak acid and write the Ka expression. Let's make it molar. Right here. Now, if it's 100% acetate here and 100% acid there, what is it halfway? Now, if we calculate or determine the pH at the VEQ over 2 right here, say we get a 4.9 hypothetically. We'll just say that's the pH at the VEQ over 2. Well, at this point, we're halfway between neutralizing all of the acid and forming all of the base. So at this point, the concentration of acetic acid is equal to the concentration of the acetate ion, or the salt being formed. Well, if that's the case, then these two are equal and can cancel out, and the Ka is equal to the hydronium ion concentration at this particular point. Well, if the Ka equals the hydronium ion concentration, then pKa is also the pH at VEQ over 2, like that. So once we determine what the pH is, we also have the pKa. So if the pH is equal to 4.9, it is also equal to the pKa. And so the analog of this to form the Ka value is now 10 to the minus pH that we have, it's equal to the pKa, our pH, and that's 10 to the minus 4.9. And so this gives us pretty close right there. You go 1.3 times 10 to the minus 5, and the accepted value is equal to 1.8 or 175 times 10 to the minus 5. So we can calculate a percent error for this determination to be the observed value, 1.3 times 10 to the minus 5 minus 1.8 times 10 to the minus 5 divided by 1.8 times 10 to the minus 5 times 100%, which is about 27.8% below the accepted value when we compare the percent error in this. For one titration, coming up with 4.9 gives you an illustration of what can be done. Accuracy in preparing solutions, of course, is a paramount concern, And if they are accurately prepared and you titrate through the entire curve, you can use and get very accurate results or numbers close to the Ka value.